In the previous lesson, we learned that the periodic table contains a great deal of information. In this lesson, you will look at additional atomic properties and see how they're all connected. And you will also look for trends among the properties. So without further ado, let's get started. Periodic trends can be the following: atomic radius, ionization energy, electron affinity, electronegativity, and etc. And we're going to be examining them in today's lesson. And let's start off with the atomic radius. Atomic radius is a measurement of the size of an atom, and it refers to the distance from the center of an atom, or the nucleus, to its valence electron. An individual atom is incredibly small, and its radius is usually expressed in picometers. 1 picometer equals 1 times 10 to the power of negative 12 meter. And in a diatomic molecule such as nitrogen, N2, oxygen, O2, or hydrogen, H2, the atomic radius is defined as the distance between two nuclei, and take the number and divide by 2. As you can tell from the diagram, the atomic radius increases down a group, since more energy levels are added, making the atom larger. And the atomic radius decreases across a period, since more protons pull the electron cloud closer to the nucleus, shrinking the atom. Valence electrons are bound to an atom by their attractive force to the nucleus. Removing electrons requires energy. By contrast, gaining electrons often releases energy. Ionization energy refers to the amount of energy needed to remove a valence electron, whereas electron affinity refers to the amount of energy transferred with the surroundings after gaining an electron. And your understanding of these concepts will be solidified along the lesson. The unit for ionization energy is kg per mole, or kilojoules per mole. You will learn more about mole in the stoichiometry unit. As there may be more than one electron that can possibly be removed, we usually specify which electron we're dealing with. For example, the first ionization energy is the energy required to remove the valence electron. Similarly, the second ionization energy, as you may expect, is the energy required to remove the next outermost bound electron. Question read: what trend can you observe in this diagram? If you look at the group 1 elements, which include hydrogen, lithium, sodium, potassium, rubidium, and cesium, we can see that as we move down a group, the ionization energies tend to decrease because the force of attraction between the electron and the nucleus decreases as the atomic radius increases. In simple words, the farther away an electron is from the nucleus, the easier it is to remove it. Look from left to right side across period. Notice that the ionization energy tends to increase, and this trend is supported by the explanation that as atomic radius decreases, the pull on the outermost electrons increases, and thus it is harder to remove them. Remember that atoms are generally smaller on the right side of the periodic table than on the left side. Following this pattern, the ionization energies for the noble gases are extremely large, and it is very difficult to remove any of their electrons. And here's a visualization for ionization energy. So basically, it decreases down a group because outer electrons are farther from the nucleus, and it becomes easier to remove. And it increases across a period because the attraction between the nucleus and electrons is stronger, and therefore more energy is needed. Electron affinity, similar to ionization energy, is measured in kg per mole. The table shows electron affinity for the first 20 elements. And again, what trends can you observe? And pause the video and use your periodic table to figure it out. As you investigated patterns in the periodic table, you might notice that the electron affinity decreases as you move down a group, and increases as you move across a period. And actually, electron affinity shows the same trend as the ionization energy. As you move to the right across the periodic table, the number of valence electrons increases, and the atomic radius decreases. And therefore, the force of attraction between the nucleus and valence electrons increases, so more energy is released when a new electron is acquired. Imagine paper clips, which represent electrons, attached to a strong magnet, which represents nucleus. You have to use energy to pry the paper clips away. And in the same way, it takes energy, which is ionization energy, to remove the electrons from an atom. And when you bring a paper clip close to the magnet, it jumps onto the magnet with a snap. And the snap represents electron affinity. And the louder the snap, the greater the electron affinity. Let's recall that the ionization energy refers to the amount of energy needed to remove a valence electron. Electron affinity refers to the amount of energy transferred with the surrounding after gaining an electron. And I hope this analogy helped. Electronegativity is the ability of an atom to attract electrons in a chemical bond. And to save a little bit of time, let me just show you the trend for electronegativity. And you guys can just do a little bit of research on this part if you like. Electronegativity decreases down a group because when atoms get larger, the attractive force decreases, and therefore the nucleus is less able to attract the bonding electrons. And electronegativity increases across a period because when atoms have more protons and are smaller, they can attract electrons more strongly. Here's a summary for this section. So basically this image covers what we have learned in today's lesson, except we didn't cover metallic character or non-metallic character. And the task is easy and straightforward, so just get a blank periodic table and determine as many periodic trends as possible. And that's about it. Thank you for watching, and I'll see you in the next episode.